Happy Super Bowl Sunday, everyone. I am going to be going through the last slide that we left off with which was, I think, slide 7 for chapter 8. And then we're going to go up through a few examples and also get through what happens when we think about work and energy with friction and do a couple examples of those. And then also maybe some possible potential energy changes that we may see in addition to what's happening with friction. So we'll probably have only one more video after this one over chapter 8, and we should be done pretty much then with chapter 8. So let's just review just a little bit in terms of the two types of systems that we talked about. We have the non-isolated system, and then we also have an isolated system. And we know that a non-isolated system is where we can have energy crossing over the system boundary, and that can happen in a variety of ways. Remember, we could have matter transfer, it could be done through work, it could be done through electromagnetic radiation, the list goes on. And ultimately, in a non-isolated system, what's going to happen is that the total energy of the system is going to change. Now, this is different from an isolated system where we're not going to have energy cross the boundary. And in this case, the total energy of the system is going to remain constant. This led us to talking about the conservation of energy, which just means that energy cannot be created nor destroyed. So if the total amount of energy in a system changes, then we know that that's due to the fact that we've had some energy being transferred either into the system or out of the system. Now, we also said that we could look at the law of conservation of energy mathematically, and that was where we said our delta E system, so our system's energy, the change in the energy of the system, is simply equal to the sum of all of the types of energy. So all of the energy that's transferred across the system boundary. So that was a way that we could mathematically show our conservation of energy. We also talked about how we will symbolize work as W, and then heat as that capital Q, and then other things we just symbolize with capital T, and then we denote in the subscript with just abbreviations. The last thing we left off with was just then talking about this isolated system, and that was where we said that the change in energy, and specifically the change in mechanical energy. So we have our delta E, and then mechanical is equal to 0. And that's because, remember, in an isolated system, we have no energy that's crossing the boundary of the system. So my total energy here should remain constant. So I don't have to worry about changes necessarily in that kinetic energy and the potential energy. Ultimately, the changes in K and then delta U should all equal 0. So let's do a couple of examples when we're looking at maybe an isolated system. Let's go to the next slide. Okay, so let's say, for example, we have a ball of mass M, and that's dropped from a height h that is above the ground, as shown here to the figure on the right. It says, neglecting air resistance, determine the speed of the ball when it is at a height y above the ground. And our system, they're telling us, is going to be the ball and the earth. So it's not just the ball, but we're saying the interaction between the ball and the earth, that whole thing is our system. Okay, so we have our ball of mass M, and we're dropping it. It's at height h to begin with. We are dropping it, and we want to know what the speed of that ball is when it reaches right here. So when it reaches at a height y above the ground. So we can say that our initial position, our initial y, our initial vertical position is h. And we know that the gravitational potential energy initially is just mgh. I know that the kinetic energy, if this ball is starting from rest, I haven't dropped it yet, is just going to be 0. I know that the final y position is going to be y because that was just the height of it above the ground. I know that the potential gravitational energy final is just mgy, because its displacement will be here. And then I know the final kinetic energy is just going to be 1/2 mv, that final velocity squared, which is ultimately what we're trying to find. So our goal here is to find that VF. Okay, let's talk about what we're going to have to do here for this problem. First of all, you could easily do this problem thinking about it in terms of like chapter 2 stuff, which was talking about kinematics. So you could definitely do this with kinematics, but we are trying to show that we can also do this by using energy terms and energy formulas based on the fact that we can think about this as an isolated system. So like we can easily do it again with kinematics, but I want us to do it using our energy stuff, our energy formulas. So they told us that this system is the ball and the earth. And they said that we're neglecting air resistance. And they also told us that there's no other force that's acting on this ball. So because we're not going to have any energy transferring, I don't have any other interaction between the system and the environment, I would say then that this system is an isolated system. And remember we said that in an isolated system, that change in mechanical energy is simply equal to 0. So since we don't have air resistance, we don't have to worry about that internal energy because we don't really have that frictional force that's really acting along. So I can think about that mechanical energy then as being my change in kinetic energy plus my change in gravitational potential energy, and all of that is equal to 0. Because remember, the change in mechanical energy is simply my kinetic energy, all of my kinetic energy plus all of my potential energy. And in this case, the potential energy would be the gravitational potential energy. So I would have delta K plus delta U, and all of that should equal 0. Okay, well, we know that the change in delta K is my 1/2 mv squared, that's final, minus my 1/2 mv squared of the initial. So I have all of that, plus I'm thinking about then my change in gravitational, that would be my final, which we said would be just mg y, because y would be that final position, and then that would be minus my initial, which is mg h, because h was then that initial position where the ball was originally dropped from the ground. So there are a couple things that we know. So we're trying to find our VF. That's my goal. I need to find that final velocity. I do know that the initial velocity, since the ball was in my hand, I hadn't dropped it yet, I know that that initial velocity was 0. So this term is just a 0. So I could think of this as then 1/2 mv final squared plus then my mgy minus my mgh, and then all of that is equal to 0. So ultimately what I want to do is solve this thing for that final velocity. So to do that, so now all I have to do is simplify then this equation to try to solve for my final velocity. So let's see what, get a new page here. Okay, so we would have, let's say we have our 1/2 mv final squared, and that's going to be equal to, let's subtract that quantity of that gravitational potential energy. So if I did that, it would give me that negative, because remember, it was just 0 over on the right-hand side. So it would be a negative mgy minus mg h. Okay, well, let's clean that up a little bit, because then that would say 1/2 mv final squared is equal to, this would make this a negative mgy, but a positive mgh. So we could just say that would be equal to mgh minus mgy. Okay, well, ultimately we're going to get this final velocity, like we said. That's our goal. And I have a masses on one side, I have a mass on the other side, so probably we'll see that those are going to cancel. But let's substitute m, and let's also just substitute g out on the right-hand side. So if we did 1/2 mv final squared equals, substitute out mg, so we would have h then minus y. So now let's divide both sides by 1/2 mass, 1/2 m. So my masses cancel. If I'm dividing by 1/2, it'll really be then like it's multiplied by 2. So my final velocity squared is equal to 2g h minus w. So if I square root that, I need to square root this. So then my final velocity is simply equal to the square root of 2g times h minus y. So we can show this also with kinematics. You could have done it that way, but this is also just showing that we can get the exact same result by thinking about it in terms of an isolated system. So our system, again, was just our ball and earth. So because it says that we're neglecting air resistance, we don't really have any other interactions from the environment acting on the system, so we can call it an isolated system. So when we said that we can think about it as an isolated system, we know then that the change in mechanical energy is simply equal to 0. And I know that mechanical energy is the sum of my kinetic energy and my potential energy. And we knew the kinetic energy, 1/2 mv squared final minus our 1/2 mv squared initial. And then we knew our change in potential energy would just be mg, our y final position minus our mg y initial position. So then ultimately we just simplified this down to solve this and rearrange this entire equation for our final velocity, and we end up with that. So let's look at another example of an isolated system. So we have a spring that's compressed to a position A here. And before we even actually start talking about this, so there's a launching mechanism of a pop gun, and that exists or consists of a trigger-released spring. So in my pop gun here, we just have a launching mechanism that's based on this spring that's right here. So the spring is compressed here to position A. So that means that we've moved a negative displacement here for position A. And then we are going to release the trigger, and then the projectile is going to move up until the spring reaches its equilibrium position here at B, and then the spring will no longer then be acting on that ball, so then the ball becomes a projectile, and it's going to leave that barrel of that pop gun until it reaches position C, where ultimately then gravity is going to start slowing it down. So at position C, we would say then that's where our velocity or our speed would be equal to 0, because remember, it will stop to change direction because of gravity. So let's just say, or let's assume then, that at position B, that's where our y is going to be equal to 0, because that's where our spring would be at its equilibrium position. And then the mass, let's say, is 35 grams. Let's say that at position A, that would be a negative 0.120 meters. And then let's say also then at position C, that's going to be at 20 meters. And they're telling us to neglect all resistive forces that are acting then on that ball. So we're not going to have friction from the barrel of the gun. We're also not going to have any air resistance. So the only thing then that I need to think about is that I have the ball that's moving with the spring because of this spring mechanism and this pop gun. So I can think about this whole thing as the system. It's not getting any interaction or any influence from any other outside environments. So this would be an isolated system. So the question asks us to determine the spring constant. So remember, our spring constant is symbolized as K. So we're trying to solve for K here. Okay, so let's talk about where we would start on this problem. Okay, so again, we know that this is an isolated system, and remember that we said that an isolated system is where we have the change in mechanical energy is simply equal to 0. Well, the change in mechanical energy is equal to the sum of all of the potential energies and the kinetic energies, and that's what's equal to 0. So we know we have our kinetic energy plus we have more than one type of potential energy that's working in this pop gun. So we have gravitational potential energy, because once that mass leaves the barrel of the gun, gravity is working on it, it's pulling it back down, ultimately then having that ball come to a stop at point C. So I'm going to say delta U G to represent the gravitational potential energy, but we also have this spring that's working with this ball. So I'm also going to have the change in potential energy. Oh, sorry guys, I didn't mean to write G. I meant to write S here. And it won't let me. Okay, we'll just write over it. So this should be S to represent spring. Okay, so we have our kinetic energy, our change in kinetic energy, our change in gravitational potential energy, plus our change in the elastic potential energy, which just means that we're dealing with a spring. All of that should equal 0. Okay, so let's kind of analyze this and kind of think about the pieces that we have. Ultimately, we know that the projectile, that ball, that mass, is starting at rest. So its initial speed is 0. So VI equals 0. I also know that at point C, the ball has completely stopped, because now it's stopping to change direction, so I know that its final velocity is also equal to 0. So if my initial velocity and my final velocity are equal to 0, what's going to happen to delta K? Well, remember, we know that's 1/2 mv final squared minus 1/2 mv initial squared. And if the final is 0 and the initial is 0, then that means delta K is just equal to 0. So now the only things that we have to worry about are the change in gravitational potential energy and the change in the elastic potential energy. And the sum of those two then should equal 0. So let's calculate the change in gravitational potential energy. So let's do that one now. Okay, so to find delta UG, we know that that's just going to be our mg final position. The final position at that ball was denoted in that figure YC. Remember, that was 20 meters. So that one was at 20 meters. And we're going to subtract that from its initial position, for my initial potential energy based on gravity, mg y sub a, because it's starting at point A, and point A was a negative 0.120 meters, so 0.120, and that was a negative meters. Okay, well, we knew that the mass was 35 grams, but that's a problem because remember, when we're thinking about, ultimately our goal is to find that spring constant K, and that's units of Newton per meter, and a Newton isn't a gram, it has a kilogram in its dimension. So we don't want it in grams, we actually want this in kilograms. So this should be 0.035 kilograms. Okay, so let's just plug our numbers in here and actually get a number for our gravitational potential energy. So that would be our 0.035 for our mass times our 9.08 meters per second times our 20 meters. And we're subtracting that from the mass, 0.35, times our gravity, times our initial position, which was a negative 0. Because remember, we compressed the spring, negative 0.0 or 0.120 meters. Okay, so if we do this, we should get delta UG to equal 6.901 joules. Okay, so we have our one piece here, our 6.901 joules. So ultimately, remember, we were left with, because we said that kinetic energy was just equal to 0, the change in kinetic energy was just equal to 0. So we have our delta UG plus our delta US should equal 0. Well, now we know what this value is. So let's talk about then delta US. Let's talk about the elastic potential energy. Okay, so how are we going to find that? We know that the change in elastic potential energy is just going to be our 1/2 kx squared, that'll be the final position, minus our 1/2 kx squared of the initial position. So we're trying to find k. So initially then, if we're thinking about ultimately, when the mass, that ball, is leaving that pop gun, we know that it's going to be at its equilibrium position. So the final position for the spring is going to just simply be 0, because the spring is going to go back to its restoring position, which is just equilibrium position, which is 0. So all of this, the final position, would just be 0 here. So really, the change in our elastic potential energy is just going to be equal to a negative kx I squared. So this is the position initially then of that spring. So we know then that that's, if we, let's rewrite this then. So we have a negative 1/2 kxi squared. If we take then our delta US, which is here, and we add it to our delta UG, remember we said that should equal 0. Well, we just found this, so we could say a negative 1/2 kxi squared plus our 6.901 joules should equal 0. Okay, well, again, we're trying to solve for k. And I know that the initial position for the spring was that negative 0.120 meters. So now let's do this and then solve for k. Okay, so again, we have our negative 1/2 k. Our position initially for the spring was at negative 0.120 meters, and that's squared. And then we're going to say that equals then a negative 6.901 joules. Okay, so ultimately, if I do my math here, we should get our spring constant, our K, to be equal to 958 Newton per meter. So our spring constant we have found based on just the change in mechanical energy for an isolated system, knowing that that then would be 0. Okay, so there's another part to this question, so let's go back and look at that question. Guys, I don't know that we can go back and look at this question based on the app that I'm using here to write this. But the other part of the question says, find the speed of the projectile as it moves through the equilibrium position B of the spring. So it says, find the speed of the projectile as it moves through the equilibrium position B of the spring. So ultimately on B, you're trying to find the speed at point B. I would like you to try this problem. I want you to try this one. Remember, we've already said it's an isolated system, so you know all of the different types of energy that's working here in this pop gun. So try this problem, and we'll look at it in class together on Tuesday after your roller coasters. So I'm going to expect that you have that one out at the beginning of class, even before we start our roller coasters. Okay, so now looking at friction. So when we think about work, when we've talked about work in the past, we always think about work involving the displacement in terms of a point of application of force. So it's like a specific point that I'm saying that this is the point where I'm doing work on a system. So friction kind of gives us a problem in the sense that friction happens because of that local adhesion of surfaces that are in contact with one another. So if we're looking at this picture over here to the right, we have to model the frictional force as this interface between let's say that we have a book and then we have that book moving across the surface. So it's actually the interface between the book and the surface. So this is where that local adhesion happens when we're talking about friction. Or they sometimes just call them teeth. So we can just model them as teeth. And let's say that these teeth are just identical here in this case. If I move this book across the surface, let's say that we move the book a certain displacement, let's say D, across the surface, I notice here that my point of application, let's say that we said that this was the interface between those 2 points. That point of application didn't really move that entire displacement. Instead, it only moved half of that displacement. So the point of application of the friction force moves through a displacement of magnitude d over 2. In reality, the friction force is spread out over the entire contact area on an object sliding on a surface. So a lot of times we can't say that the force then, or we can say, we know that the force is not localized at a particular point. So it's hard for us to model work for friction as a specific point of application of a force. So because the magnitudes of friction forces at various points are constantly changing as that local adhesion occurs, then the surface and the book, they're going to deform locally based on these local adhesions. So the displacement of the point of application of the friction force is not calculable. And so neither is the work done by the friction force. So it's really hard for us to find work done based on friction force just because we have different places for local adhesion of friction, and it's hard for us to see that, and it's hard for us to calculate that because every surface is different. So the work kinetic energy theorem is valid for a particle or an object that can be modeled as an object, but when friction acts on it, you cannot calculate the work done by friction. We still, though, can think about calculating friction based on Newton's second law, so that's going to be a valid system for us to use, even though our work kinetic energy theorem really is not going to be. Okay, so let's say then that we have a problem where it says that friction is now acting on a system. So if we do run into that, then we can say that delta K is that change in kinetic energy is equal to the sum of the work done by all of the other forces minus that frictional force times the displacement that frictional force has gone through. So we know that a friction force is going to transform ultimately kinetic energy into internal energy. Because remember when we talked about when we're sliding a book or sliding anything really across a surface, we feel something like on our hand, or we feel a change in temperature. So that friction force is transforming kinetic energy into internal energy. So because of that, we can get this formula here, which should say our change in internal energy, which really has to do with that frictional force, is simply equal to the kinetic friction times that displacement that the kinetic frictional force has done. So change in kinetic energy should be equal to the work done by all of the forces other than friction. So that's what I get when I'm looking here. So I'm going to get that change in kinetic energy is equal to the sum of the work done by all other forces minus then what's happening with friction. So in general, we can say also, or we can write this equation that the sum of the work done by all other forces is simply equal to work, which is equal to my change in kinetic energy plus my change in internal energy here. So that's just thinking about this and just rearranging it in a different sense. Okay, so this is representing a non-isolated system, because with a non-isolated system, we're going to have some types of energy that's being transferred. And also when we are talking about non-isolated systems, this is specific too for when we have a non-conservative force acting on our system as well. So friction, remember, is a non-conservative force. So it is path dependent. And this is different than our conservative forces, which ultimately just depend on the initial position and the final position. All right, this will be the last example that we'll do for this video. We'll pick up next time doing a couple more examples for dealing with work in terms of friction as well. And then also kind of doing a couple more examples when we're finding that there's also changes with potential energy in terms of work done. And then we'll end with power and then how we calculate power, and then just maybe one example of doing a problem with power as well. Okay, so for our last example, we have a 6 kilogram block that's initially at rest, and that is pulled to the right along a horizontal surface. So I have my block here, and we're pulling it with some applied force here over to the right. And it's a constant force, and that constant force is going to be of 12 newtons. We want to find the speed of the block after it has moved 3 meters if the surfaces in contact have a coefficient of kinetic friction of 0.15. So let's talk about how we would set this up, because now we have friction in play, so we have to think about our formula here for friction, or using friction. Okay, so we know that the sum of work done by all of the other forces is equal to the change in kinetic energy plus the change in internal energy. And we said before on one of the previous slides that the change in internal energy, that's where we're getting our friction, because friction is what's going to cause some change in internal energy. And that's just simply equal to that kinetic friction times the displacement. Okay, so let's think about the work that's being done by all of the other forces. So remember, we had this block, it was on this surface, I have an applied force here, I have the normal force acting that way, of course we have our weight force directed downward, and then we have that frictional force, which should be a K there, sorry guys, we have that frictional force. So we can't think about friction because it's the work done by all of the other forces other than friction. And we know that the block is moving horizontally. So the normal force and the weight force aren't going to do any type of work on the system, because their points of application would be vertically when our point of force causing the displacement is horizontally. So the only really force that we have to deal with for the sum of the other forces that are doing work is really just this force right here. So I would say then that the sum of the work done by the other forces, I'm just going to call that OF, other forces, instead of writing that out, it's just going to be equal to the force times that displacement. And since the displacement and the force are directed in the same direction, then cosine would just be 0. So cosine 0 is just 1. So we can just say then that work done based on our applied force is just force times that displacement. So the sum of the work done by all of the other forces, we know that the applied force was 12 newtons. So 12 newtons times that displacement, which they said was 3 meters. So that means the sum of the work done by all of the other forces should be equal to 36 joules. Okay, well, ultimately, this is, again, the problem asked me for the speed of the block after it moved that 3 meters. So if it ended right here at that 3 meters, what was the speed? Well, I know I'm going to find speed using my kinetic energy, but I at least found one part here. Ultimately, I'm going to use this part to find speed. Could we go ahead and find then the change in internal energy? So we know that the change in internal energy is equal to that frictional force times the displacement. Well, friction force, we know, is equal to mu times the normal. And when we were looking at our surface again, there's our block. We had the normal. We had our weight force. If we're thinking about things that are acting in the y direction. And then in the x direction, we had our applied force and then our force of friction. Okay, so the sum of the forces in the y direction should be equal to the normal minus mg. And since they're not accelerating in that y direction, they should be equal to one another, so that should just be equal to 0. So normal equals weight force mg. So then I could say that the force of kinetic friction is equal to mu times mg. Well, they gave us mu. They told us that that was 0.15. And we know the mass of the block is 6 kilograms. And we know the acceleration due to gravity is 9.80 meters per second squared. And if we want to go ahead and find that internal change in internal energy, then here's my frictional force. If I also multiply that by the displacement, which was 3 meters, that will give me that change in internal energy. So if we do all of that multiplication, our delta E internal should give us 26.5 joules. Okay, so let's go back and review what we have. Ultimately, we said the sum of the work done by all of the other forces is equal to the change in kinetic energy plus the change in internal energy. And remember that change in internal energy is done by friction. We already calculated the sum of the work done by all of the other forces because we said that the only force that's working on it based on its displacement is the applied force. We found that to be 36 joules. That equals my change in kinetic energy plus that change in internal energy, which is the ultimately what frictional force is doing, and we found that to be 26.5 joules. Okay, so our goal is to find that final velocity. So let's go ahead then and say, let's go ahead and make this simpler. So our 36, let's take our 26.5 from that other side. So we would have 9.5 joules equals delta K. And we know that that delta K is just equal to 1/2 mv final squared minus 1/2 mv initial squared. Well, the problem said the block started at rest, so the initial velocity must be 0, so that takes this part of that equation completely out. So now I can say 9.5 joules is equal to 1/2 the mass, which is 6 kilograms, times that final velocity squared. So then if I took my 9.5, divided it by 3, and then square root, we should get our final speed to be equal to 1.8 meters per second. Yay! Okay, so this will be the problem that we'll end on. Again, I'll be posting another video doing some more examples over chapter 8 tomorrow. And I don't know that we'll get to kind of starting on problems with chapter 8 until Wednesday in class, but I am going to post some practice problems from chapter 8 tomorrow, just so if you want to get a head start on them, you absolutely can, but it's not required. That's just if you want to get a head start on them. I'm also going to be posting a pretty rough schedule for the week because things may change a little bit. Just seeing kind of how we progress through chapter 8 in class on Tuesday, Wednesday, and into Thursday. So I hope you guys have a great Super Bowl Sunday, and I will see you tomorrow. Bye.